today's lecture. Today we are going to look at an overview of geologic structures, all right? And that is the last topic more or less we have for the semester. Is that clear? All right. So for the case of glaciation, you could read that for your own consumption, all right? But overview of geologic structures is the last examinable topic. All right, so in geology, when we talk about structures, we can talk about three main structures: primary structures, secondary structures, and then compound structures. All right, primary structures, secondary structures, and compound structures. All right, so what are primary structures? So they are those which develop at the time of formation of the rocks. So for instance, in sedimentary rocks, we know that we could have some bedding plains and all that, right? And then some volcanic structures. So this type of structures develop at the same time when the rocks were being formed. So we call these structures primary structures. Primary structures. And then there are some structures that develop after the rock was formed, right? And we call those structures secondary structures. Secondary structures. All right. So we have primary structures and then secondary structures. And secondary structures are those that develop, the structures that develop in the rocks after their formation as a result of their subjection to external forces. All right. Like jointing, is that not it? So whether tension or compression. So those are secondary structures. And then we can talk about compound structures. Compound structures. So compound structures formed by a combination of events, all right, some of which are contemporaneous, which means that they form at around the same time as the formation of a group of rocks are taking place in these structures, all right? And we call this compound structures. So these are a combination of events which may happen at the same time or around the same period as the rocks were formed. So those are compound. So we have primary structures, secondary structures, and compound structures. In terms of stresses, we know that we have tensional stresses, right? So we have tensional stress where we are pulling apart an object. We could have compressive stresses. So here we have compressional forces involved, and then we could have shearing, all right? So these are the forces that a rock mass is subject to. And strain is the change in the shape or size of a rock in response to stress. All right. So when we talk about strain, it means that we have a deformation. Is that not it? So change in length over length gives us strain, right? So we could talk about elastic deformation and plastic deformation. Anytime a rock deforms and then the rate of deformation is directly proportional to the applied stress. All right, then we say the deformation is elastic. The rate of deformation is directly proportional to the applied stress. Then the deformation is elastic. So for elastic deformations, it can return to its original size once the stress is removed. All right, it can return, the object can return to its original size once the stress is removed. So we call that kind of deformation elastic. Then again, we could have plastic deformation. On the other hand, that is going to result in a permanent change in the size and shape of the rock, even after the stress is removed. So that is plastic deformation. All right. So in elastic deformation, the object can return to its original size. Plastic deformation, we have a permanent change in the size and shape of the rock, even after the stress is removed. All right. So after deforming plastically for some time, the rock may finally break suddenly. And that type of deformation, we call it brittle. Brittle. You know, something that is brittle can easily break, right? So we call that brittle deformation. So with respect to the factors that could affect how a rock deforms, we could talk about the depth. In other words, lithostatic pressure and heat, right? We could also mention time, then composition of the rock, and then fluids, all right? So a rock may undergo ductile deformation when we subject it to stress at a certain depth within the earth, where we have very high temperature and pressure, or we have a lot of fluids. But that same rock may undergo brittle deformation at shallow depths. All right. So the type of deformation, whether ductile or brittle, elastic or plastic, depends on the depth, the time, the composition of the rock, and fluids. All right. So we could talk about measurements of geological structures. There are two main structures we are concerned with. So these structures, we call them strike and then the dip. All right. Strike and dip. So what is strike and dip? All right. What is strike and dip? So here we have the strike, right? Which is like the general trend. You see, this is the strike of the rock. So if you stand in this east-west direction, I have the strike, right? Then downwards, this is the dip direction. So if you pour water at this surface, the direction it will follow, this is the dip direction. If I pour water or a handful of sand at the top here, the direction that water will follow is the dip direction. In this other opposite, 90 degrees from the dip direction, we have the strike, which is, in this case, we can call it the east-west. All right, that's the strike. So we use the geologic compass to measure the strike and the dip of geological structures. And these are very important. All right. So we are going to start by talking about secondary structure. And then after that, we'll talk about primary structures and finally compound structures. So what are examples of secondary structures? So we have folds, right? So a fold, which is a form of ductile deformation, all right? Ductile deformation, not a sudden break. Then we could have fractures, and fractures are represented by faults and joints, and which generally result from the brittle behavior of rocks. When we have ductile deformation, we are going to form a fold, all right? So folds are bends or flexures in the Earth's crust, and they can therefore be identified by a change in the amount or deep direction of the rock units. All right. So we need ductile deformation of the rock. And normally this happens because we have compressive or shear stresses, right? So in the previous slide, I showed you the difference in the types of forces we have. This is tensile, compressive, or shear. So for you to form a fold, we need a compressive force or shearing forces, all right? Compression or shear. All right. So this is a typical fold. This is a real world picture. You see the way the rock is deformed, right? It has been folded. Is that not it? So this is a geologic fold. Geologic fold. And when we talk about a geologic fold, we see that we have it going up and down, then up. Like you climb up to a mountain, you come into the valley, and then you climb up again. All right. So these two sides, the opposite sides, we call them the limbs of the fold. The limb, this is the limb of the fold, all right? Like the legs of the fold, the limbs of the fold, is that not it? Where the two limbs meet, we call that the hinge. It's like the hinge of a door, right? The hinge line, where the two limbs meet, all right? And the plane associated with that hinge line, it's called the axial plane. Axial plane, all right? And then we could also talk about the various hinge points. So along the hinge or axial surface, we could define the hinge points, right? The hinge points, all right? And then we have the inflection point, which is the points, you remember from your calculus, we have the points of inflection, right? Which is the point at which we are changing, right? We are changing from, say, a hill to a valley, all right? We are from getting into a trough. That is the point of inflection. So here we have another point of inflection because it's going from a valley to a hill, right? And then here, another point of inflection, it's changing again to a valley or a trough. So these are the limbs of the fold, the axial plane, and the axis of the fold, all right? And this is a real world example of a fold. You can see clearly this kind of feature or structure will result from compressive or shearing stresses, all right? It's like you compress the rock by applying force, right? So it's like you apply force in this direction to the rock and then apply force in this direction. So this is compressive in nature. So we produce this fold, all right? We produce the fold. That is folding, all right? Folding. So in effect, we just discussed some key features of a fold, right? We looked at the hinge line, which is the line of maximum curvature on the folded surface. Is that not it? The hinge line, all right, which is the line of maximum curvature, right? And then we also look at the axial plane. And it's an imaginary plane dividing the fold into two equal parts known as limbs. So the axial plane divides the fold into two equal parts known as limbs, all right? Then we have the crest of a fold. So the crest of the fold can be considered the highest point on the folded surface. And the trough is the lowest point. The crest is the highest point, and the trough is the lowest point of the fold. So you know crest and trough, right? And the interlimb angle, is the angle between two limbs of the same fold. The angle between two limbs of the same fold. We could also talk about the angle of plunge of a fold, the angle of plunge of a fold, all right? And it's the angle between the fold axis and the horizontal plane, all right? The angle between the fold axis, the axis of the fold and the horizontal plane, all right? And that is what we are referring to. This is the fold axis, is that not it? The fold axis, all right? The fold axis. And then we could talk about the interlimb angle. This is the angle we are referring to as the interlimb angle. Interlimb angle, all right? Interlimb angle, all right? So the interlimb angle is the angle between two limbs of the same fold, all right? It is measured in a plane perpendicular to that of the fold axis. So the angle between the two limbs, this is one limb and one limb, right? The angle between them is the interlimb angle. These are the limbs, right? So the angle between these two limbs is the interlimb angle. Interlimb angle, all right? And then we already defined the crest of a fold, all right? The crest of a fold, which is what? The highest point is the crest of the fold, right? The highest point. And then we have the trough and the crests. All right. And then we have the median surface, the surface that passes through points where the fold limbs changes its curvature from concave to what? Convex. All right. So the surface that passes through the point where the fold limb, the limb of the fold is changing its curve from the concave to convex. We call that the median surface. And also the amplitude of a fold is the vertical distance between the median surface and the fold hinge. All right. And then because folds are like waves, we can also talk about the wavelength. which is the distance between two consecutive crests or troughs. All right. So you see, this is the wavelength, right? It's the distance between two consecutive troughs or crests, right? Can you see from this point, the middle of this trough to the beginning point, the middle of this trough gives us the wavelength. Or I could take it from the middle of this particular crest, the middle of this crest, that is the wavelength, right? Wavelength. And this is the interlimb angle. All right, this is the limb. These are the two limbs of the fold. The highest points, the crest, and the axis here at the crest, we call it the fold axis. Fold axis. All right. So how do we classify folds? We can classify the folds based on the direction of dip of the limbs, right? So based on the direction of dip of the folds, of the limbs of the fold, we can classify the fold. All right. So in terms of this classification, we have terminology such as antiform, and then synform, antiform and synform. All right, antiform and synform. So if both limbs dip towards the fold axis, we have a synform. All right, so I'm going to show you pictures of antiforms and synforms. We also have anticline and syncline. So we have antiform and synform, anticline and syncline. All right, and then we also have one we call a monocline. A monocline. All right, so let's see if we can look at images of this. So we can also classify based on the inclination of the axial plane. Based on the inclination of the axial plane. All right, so we can, the first classification we said based on the direction of the limbs, right? Based on how the limbs are oriented. Then we can also classify based on the inclination of the axial plane. All right, based on the inclination of the axial plane. And we showed what the axial plane is. So now I believe we can all picture the axial plane, right? Based on the inclination. So if the axial plane is inclined at an angle less than 45 degrees, all right, the fold is said to be inclined, all right? If the axial plane is greater than 45 degrees, then we are going to say that the fold is inverted or overturned, something like that, all right? Something like that. Then we could also talk about classification based on the value of the interlimb angle. So you remember we talked about the interlimb angle, right? So if we say an open fold, it means the interlimb angle, which is the angle between two limbs of the same fold, is greater than 70 degrees. All right. If the interlimb angle is between 30 and 70 degrees, we call it a closed fold. So we have open fold, closed folds, all right, tight folds, meaning the interlimb angle is less than 30 degrees. Then we have isoclinal folds, have a zero interlimb angle. All right, zero interlimb angle. So the interlimb angle we said is the angle between two limbs of the same fold, right? So the angle here, you see, if I take this is one fold, right? So if I take the angle here, all right, if I take the angle, so here we can see this is a real fold, is that not it? So if I take this, all right, and I measure this angle here, this angle is the interlimb angle. So depending on the value of the interlimb angle, I can classify this the particular how do you call it, the fold, into open, closed, isoclinal, all right, based on this angle. This is a fold, is that not it? We have a fold, all right, we have a fold. So here we have what? The crest and the trough, the crests and the trough, right? When we have it in this kind of shape, like a hill, we call it an antiform. Antiform. All right. And then when we have the fold in this form, we have a synform. Synform. So we have antiforms and synforms. Is that not it? So here we have what I just drew is an antiform. Antiform. And now this is what? The synform. And then I have an what? And what? How do you call this? I have a synform and then an antiform and then a synform again. All right. So I'm taking that again. So here, this is what? A synform. Synform. Right? Which is like the U shape. Then the sort of N shape, I'm going down. So this is an antiform. Then I have a synform again. All right. So synform, antiform. Then we have a fold. All right. And we can also synonymously, we can say an anticline or what? A syncline. So this is a syncline, right? Syncline and what? An anticline. All right. So when we talk about synform and antiform, in this case, we are looking at the shape, right? The shape of the fold. Is that not it? So here this shape gives us an antiform. The U shape gives us a synform. All right. Alternatively, we can say anticline or syncline if we are considering the ages of the rocks. So when we have older rocks in the middle here, we say it's an anticline. If we have younger rocks, we call it a syncline. All right. So this is a syncline, anticline, or synform, antiform. So synform is like a U, anticline is like an N. All right. Synform is like a U. Great. I believe the concepts and this forms the results of compressive forces. So we already discussed the type of faults we have, right? We could have normal faults, all right, reverse faults or thrust faults. So you remember we said that when the hanging wall moves downwards relative to the footwall, we have a normal fault. And in a reverse fault, we said the hanging wall is going to move upwards relative to the footwall. A thrust fault is a special type of reverse fault in which the fault plane is dipping at an angle less than 45 degrees. All right, less than 45 degrees. So let's look at the other types of faults we could have. We have a strike slip fault. A strike slip fault. So it's a fault in which the movement is horizontal along the strike of the fault plane. All right. Then we could also have an oblique slip fault. Oblique slip faults. So these are other types of faults, strike slip and then oblique slip. All right. So in an oblique slip, we have displacement in both the strike and dip directions. Do you remember we discussed strike and dip, right? Strike and dip. So we said that if I have a particular bed like this, this is going to be the strike, right? And then down here is going to be what? The dip. All right. Strike east west, and then we have the dip. All right. But the main faults or the main faults you should focus on are the normal fault and the reverse fault. And a special type of the reverse fault is the thrust fault. Now let's look at some typical examples. See here, we have a normal fault because the hanging wall has moved down, right? The hanging wall has moved down. So we have a normal fault. Then we could have a thrust fault or reverse fault. All right, we have a reverse fault when the hanging wall moves up. When the angle is less than 45, we have a thrust fault. Is that not it? So with the thrust fault, we said that the fault plane is dipping at low angles, less than 45 degrees. All right. And then we have these other types of fault. How are we able to identify faults in the fold? How do we identify faults in the fold? So there are three things we have to talk about: fault drag, the fault breccia, and the slick inside. Slick inside. What is a fault drag? All right. So we have a small scale folding because we have one big block moving on the surface of the fault plane. Is that not it? And we call that the fault drag. All right, the fault drag. We could also have tiny broken pieces. Tiny broken pieces. All right, along the fault plane, broken into angular shapes or pieces, like fragments. They may be further crushed into powder. All right. Tiny pieces. We call that fault breccia. Fault breccia. They are like tiny pieces of rock on the surface of the fault plane, fault breccia. And you see, if you wrap something roughly against another surface, we are going to have a frictional drag, right? And because of this frictional drag, the plane is going to become highly polished or abraded. Is that not it? And we call that slick inside. Slick inside. If I drag something on another surface, two surfaces, all right, one surface is dragged on the second, we are going to have this highly polished surface because of the dragging, and we call those slick insides. Slick insides. So we have fault drags, which are like small scale folding, all right. The breccia are tiny broken pieces of rock on the surface of the fault plane. And then we have slick insides, which are what? Polished surfaces or abraded striations or surfaces because of the frictional drag, all right. In terms of joints, you remember we define a joint as a fracture along which no movement has occurred. So what are the types of joints we have? We have columnar joints, which are like joints that are formed in basalt, all right. I'm going to show you examples of this type of joints. We have mud cracks. So you see, when you see the surface of mud, right, or clay, sometimes when you're walking, you see a surface. When mud dries, you see cracks in it. Is that not it? We call that mud cracks because as the mud loses its water, it contracts and cracks. It contracts and cracks. So we call that what? Mud cracks. Mud cracks. Then we could have secondary joints that form in rocks as a result of their subjection to any form of stress. That could be compression, tension, or shear, right? And joints that are oriented in one direction approximately parallel to one another make up a joint. So if I have joints, a joint is a break in a rock, right? So if I have joints like this in the same direction, we call this one a set of joints, all right? Joint set. And if I have another one like this is another set. So here I have two sets of joints. One is going this way, the other one is going this way. All right. So those are joint sets. Joint sets. Then we could also talk about sheet joints. Sheet joints. So this type of joints form in granitic rocks in the deserts. All right. So then we see that the rock is breaking into parallel sheets, and we call those sheet joints. Sheet joints. So these are real world examples of the joints I'm mentioning. These are columnar joints. You see, they are vertical in basalts. We have horizontal joints in bedding planes, right? Or bedding planes in sedimentary rocks. Horizontal joints. Then we have these varied sets of joints. Some are vertical, horizontal, right? Inclined. And then we also have orthogonal. Orthogonal means 90 degrees, right? So we have this orthogonal joint sets. So you remember we talk about three types of structures, right? We talk about primary structure, secondary structures, and then we also talked about what compound structures. Is that not it? Compound structures. So now we said primary structures are structures that developed at the same time as the rock when the rock was being formed, right? Like most sedimentary structures. Then we talk about compound structure. So we looked at secondary first, the various joints we looked at and faults, these are all secondary structures, right? Now we are coming to look at compound structures. All right, compound structures. So compound structures, we know they are the combinations of how do you call it, jointing, is that not it, or structures. So for instance, we could talk about unconformities. We already dealt with unconformities, right? Angular unconformity, disconformity, nonconformities. They are all examples of compound structures. Then we also have some structures that are associated with plate tectonics. So divergent boundaries, you know, we have a lot of extensional structures, all right? We have a lot of tensional structures. Is that clear? Tensional structures. All right, examples, we call them hosts and grabens. Hosts and grabens. Tensional structures. What is a host and graben? So if I have a fault plane, all right, and then I have one block, two faults, all right. Think about this as a fault plane. And this particular middle block, this one, has gone inside. Can you see? There was one fault here, one fault here. So the middle one has gone in. All right. So this is what we call hosts and grabens. Hosts and graben. All right. So this becomes the host, this is the graben, right? Hosts and grabens. All right. So then at convergent boundaries, we have folds, folding, is that not it? A lot of folding at the convergent boundaries. Then we could talk about the transform boundaries, where we have strike slip faults and then an echelon fault. So these are different types of faults at the transform boundaries. So in effect, we are trying to say that we have different types of compound structures at each of these boundaries. All right. So you remember there's something mountain building. You remember we talk about the Andes Mountains, the Himalayas, and all that, right? So the process of mountain building, the geologic term for that is orogeny. All right. Orogeny. Is that clear? So orogeny is the, how do you call it? Orogeny is the mountain building process. Orogeny. All right. Orogeny. So examples, we can talk about the Andes, the Rockies, the Himalayas, the Alps or Appalachians. These are all mountain building processes, orogeny, all right? Then we could look at vertical movement of the earth. So we call that uplift. It's like the whole land has been lifted upward. So we call that uplift, all right? Uplift. So uplift is when a landscape is pushed up from below, usually over a very large area. We call that uplift. Uplift, all right? And then there's something else we call isostasy. Isostasy. So what is isostasy? All right, what is isostasy? So isostasy is the state of balance between extensive blocks of the Earth's crust, all right, which rise to different levels and appear at the surface as mountain ranges, plateaus, and plains. So it's like a type of what? Balance, a state of balance between blocks of the Earth that are rising to different levels, all right? So what is an important effect of isostasy? We see this when material is eroded from a mountain and it results in a rise of the crust mantle boundary. You know, we said there's a discontinuity between the crust and the mantle. We call that the mohole. All right, the mohole. So uplift, we are referring to the process whereby the earth crust, all right, or the landscape is lifted up, all right, due to a tectonic process. All right, due to a tectonic process. We call that what? Uplift. Uplift. And then for isostasy, it's just some kind of gravitational equilibrium, all right, between the Earth's lithosphere and the asthenosphere. Is that clear? It's just some kind of gravitational equilibrium, all right, gravitational equilibrium. So isostasy is the rising or settling of a portion of the Earth's lithosphere that occurs when weight is removed or added in order to maintain equilibrium. So isostasy is the rising of a portion or settling of a portion of the Earth's lithosphere. So it will rise or settle. All right, the process by which we have a rising or settling of a part of the Earth's lithosphere when weight is removed or when weight is added in order to maintain equilibrium. All right, in order to maintain equilibrium. So that is just isostasy. So it's a gravitational equilibrium. So where we have a part that is not in equilibrium, the part of the Earth may rise. That part will rise to create equilibrium. All right, or it may lower. So we can form a mountain or we can form what? A plain. All right, and that's it, isostasy. Isostasy, the rising or settling of a portion of the Earth's lithosphere that occurs when weight is removed or added. All right, isostasy. Now we can talk about primary structures. Now we can talk about primary structures. All right. So what are primary structures? We said they are structures that form at or shortly after the time of formation of the actual rock. And they are very important for a number of reasons. One, primary structures allow us to determine the original facing direction of the strata. We get to know the original state, how the rock formed originally. All right. It also helps us to know exactly when the rock began to deform. So that is a primary structure. We get to know when a rock, with the aid of the primary structures, we can tell exactly when a rock began to deform. Primary structures, for example, fossils, we can use that in age determination, right? You remember the principle of a faunal succession and all that. So we can use these primary structures in determining the age of a rock. All right. Also, the primary structures can help us to interpret the conditions under which the rock formed. All right. Because of this, it is really important to identify primary structures. And we need to try to separate the primary structures, which are the structures or features of the rock that's formed at or shortly after the time of formation of the rock itself. We need to try and differentiate the processes that happened when the rock was being formed from the processes that happened after the rock was formed. And we call those secondary structures, or we could even have compound structures, resonances, like unconformities, right? These are all compound structures, unconformities. But secondary structures, you remember we discussed joints, faults, various types of faults and joints, all right? So what are examples of primary structures? Examples of primary structures include bedding planes. Bedding, like, in the course of formation of sedimentary rocks, based on the principle of original horizontality, we know sediments are deposited in what? Horizontal or nearly horizontal successions, right? So these layers, bedding planes, are primary structures. Then we could also have graded beds. So graded beds means that we could have like coarser particles coming first, all right? So when we talk about a graded bed, all right? So if I have these coarse particles in the sedimentary rock, followed by this, all right? You understand grading, is that not it? Then this, you see the size is reducing upwards, is that not it? The size is reducing upwards. So this is grading. All right, this is grading. So I start from fines one, then I come to the next size and the next size and the next size. So that is what's grading. So when we have this kind of stuff, we call it a graded bedding. All right, graded beds. It means the coarser particles are below or above, followed by the next size and the next size and the next size. That is graded bedding. And bedding planes, all right, bedding planes, we are just referring to the horizontal, the plane, right, between two sedimentary strata. Then we can have cross bedding, all right, cross bedding, then soil marks, channel structures, mud cracks. So these are various features that we find in sedimentary rocks, all right, various features we find in sedimentary rock, all right. We could have this kind of a cross beddings, all right, cross beddings. And there are various features we find in sedimentary rocks. So we could look out for examples of this, all right. Then we could also, you remember fossils? Fossils. So fossils are also examples of primary structures, right? Then we could talk about dewatering structures, then soft sediment deformation, all right, and then reduction spots. So we have a lot of examples of primary structures in sedimentary rock, all right, a lot of them, all right. At least you should know some of them, like bedding, graded bed, I explained it here, ripple marks, all right, cross beds, then fossils, watering structures, features like raindrop imprints, volcanic bombs. So these are all structures that formed at or around the same time as the rock was being itself was forming. So we call that primary structures. Primary structures. All right. So these features formed or around the same time as the rock was forming, like this graded bedroom I sketched. All right. Great. Then we could look at examples of primary structures in what igneous rocks. Columnar jointing, and I believe I showed you examples of columnar jointing, right? So this is columnar joints, all right? Columnar joints in basalts, right? Columnar joints in basalts. So this is an igneous rock and a primary structure in these basalts, all right? Primary structure. Then we could also look at flow surface features, all right? Flow surface features and pillow basalts or pillow lavas. When we have an eruption into water, all right, we could form pillow lavas or pillow basalts. All right. So these are the basically what we need to know about geologic structures. That's basically we have primary structures, secondary structures, and compound structures. All right. Primary structures formed at the same time as the rock was being formed. Secondary structures developed later on, like joints and faults, right? Then we could also have compound structures. All right. So in the case of the compound structures, we look at unconformities, structures that develop associated with plate tectonics, and each boundary divergence, we know we are having tensional structures. Convergence, we are having folds because of the compressive forces. And the transform is like shear, all right? So we have strike, slip, faults, strike, slip, faults, all right? And we said orogeny is also an example of compound structures where we have mountain building associated with the tectonic plates, convergence, right? Then we define uplift as the process by which the land below is pushed up, all right? And then we said, as far as isostat is concerned, it is the rising or settling of a portion of the Earth's atmosphere, or not atmosphere, lithosphere, sorry. All right, the rising or settling of the Earth's lithosphere that occurs when weight is removed or added. So if there's an imbalance some part of the land surface is going to rise up to create equilibrium. Or if the need requires, naturally, we are going to have a lowering of a land surface to create what? The state of equilibrium or balance, all right, between the extensive blocks of the Earth's crust. And we call that isostasy. So it's a state of balance, all right. So, and then the examples of primary structures, we mentioned bedding planes, graded beds, ripple marks. I illustrated some of these, all right. And then fossils. And then in the primary structures in rocks, igneous rocks, we could have columnar joints and flow surface features and pillow basalt. So all these ones, in metamorphic rocks, it depends on whether the rock was initially igneous or sedimentary. We are going to see some of these structures being retained, all right, being retained. If it's an igneous structure, you may still see them in the metamorphic. And you can see some sedimentary structures, all right, in metamorphic rocks, if the rock was originally sedimentary, all right. Great. So with this, this particular brings us to the end of overview of geologic structures. Any questions? Any questions? Any questions?